Perez for having me here, and also especially thanks to Aida for the invitation. So yeah, this is going to be a little, I will do what I can because Lattice is an enormous subject, and I'm not going to cover it all, of course. So what I'm going to tell is things that I myself had joy doing Lattice, okay? Which is more theoretically oriented kind of things, and I'm going to try to explain them in a way that is accessible and make some connections with things that are going on in the HepTH community, which I think may be interesting maybe for everybody. But so I will basically talk as the joy of Lattice as a theory tool for investigating things that we don't know about non-perturbative quantum field theories. But before doing that, I want to do a little bit of a summary of well, what Andreas showed very well in the colloquium last week, which is the fact that Lattice is really a precision tool for doing QCD and a precision tool for doing QCD input for processes that are important for standard model processes, right? So I will just go through a list of things that the Lattice has done in recent years mostly, which are important and challenging. And the Lattice has been really very precise in getting numbers there. So I will just light some numbers that Andreas has also covered, but I think it's important to reflect them in this talk, even though I'm not going to talk about that. I know Marina is going to do a talk next week about G-2, which is the first thing that I'm going to highlight. So she will give all details, I guess, about that. No? So let me start with, yeah, a precision tool, right? For QCD. And there are a series of things, as Andreas told us, that the Lattice has been able to compute with very high precision. And I think in the recent years, the thing that has had more impact is what is related to the G-2 of the muon. And to remember a little bit the story, if you go back to 2021, the situation was basically that dispersive approaches that are not Lattice methods showed versus experiment a discrepancy of about 4.2 sigmas, right? Around 4 sigma discrepancy. So this G-2 was looked at as the place where we were more close to find sort of new physics input, right? However, also in 2021, I mean, at this moment, most Lattice results, Lattice was aiming at this number, at the G-2 of the muon, but the results were not precise enough to compute with the dispersive analysis, right? But then at this time, there was a Lattice result by the BMW collaboration, which in principle seemed to be competitive within errors with the dispersive approaches and gave a number that was on top of the experiment. Well, I don't remember either, 1.5 sigmas or I don't know, whatever, of the experimental approach. So this was a challenge. In principle, just one Lattice number is not a challenge. It can be wrong. But this moved the Lattice people, the Lattice community. I mean, there were many people trying to compute this quantity. It's extremely difficult. The part that enters here is the hadronic vacuum polarization that is most difficult to compute. And there were a number of Lattice groups trying to determine this number, right? So as of today, there are other Lattice collaborations that have been able to reproduce the BMW, well, to recompute this quantity fully. Some of them fully, some of them in parts. And all of them agree with experiment and with BMW. So at the beginning, one would think this is a challenge for theorists, why the dispersive approach is giving a number that is different from the Lattice approach. But the thing has complicated even more with new experimental results for E plus E minus into pions by a collaboration that is called CMD3. That when you combine it with the dispersive approaches, again, give a number that is compatible with experiment. So now the challenge is in the experimental, I would say, field. They have to clear up what is going on there. And as I said, Marina is going to present a summary of, I guess, Lattice results and everything next week. So you will hear a lot about that there, okay? But I think, well, this is an example of a number that the lattice has produced and has had a tremendous impact, okay? It's really, well, something I would say very impressive. I don't work in these things at all, but I think it's really impressive. So more things that we can, by the way, interrupt me any moment, ask questions, whatever you want, okay? If I don't get to the end, I don't care, so please feel free to ask questions. So second thing that I think the lattice has been very good at is in the computation of the strong coupling constant, alpha strong. Basically what we measure is the lambda parameters in units of a hadronic scale. And at the moment, lattice numbers are able to give this number with a precision, I think, of about 4%, which implies about 1% in the determination of alpha strong at the scale of MZ, right? And the lattice numbers appears in the PDG, and they are the most precise determination of alpha strong in the PDG, with an error that is comparable to the average of all other determinations in the data book. So Lattice is also doing a tremendous work here in the determination of alpha S.
What's the current lattice precision?
Sorry?
What's the current limit? Like, what sets the limit on lattice precision?
Well, I would say here, continuum limit extrapolations and isospin breaking corrections probably, I don't know how much they influence alpha S, but probably also yes.
The most odd one stresses that measure statistics.
Statistics also, you say? Yeah.
For the step scaling.
For the step scaling, well, there is an issue with the kind of scheme that you use, no? Gradient flow schemes have larger errors, so they have to switch typically to the, and then there is also the issue of, yeah. It's Schrödinger functional, no? You say.
The latest alpha result matches the gradient flow step scaling to the traditional Schrödinger functional step scaling to avoid the issue.
Yeah, they match. I mean, they use first, to connect with mu hadronic, they use first gradient flow, and then they match to a Schrödinger functional to run to the perturbative regime. So the thing is that the thing that happens with alpha strong is that you want to connect to a hadronic scale, right? But if you want to compute a hadronic scale on the lattice, you are limited by two quantities, which is on one side that you have a finite box, you put the theory in a box, and then the lattice spacing, right? So there are two cutoffs in the theory, and your mu hadronic has to live within those two cutoffs, okay? So in principle, you are limited from above by the ultraviolet and from below by the box. So if you want to put in one box the hadronic quantity and also the perturbative domain where you match to lambda ms bar, you have an issue, right? Because this is typically, I don't know, 2 to 5 GeVs. And then you have an issue to match all these quantities in the same box. So the strategy that these people that do step scaling are using is that they use different boxes to measure mu hadronic and to run to the perturbative domain. So they go on in steps. I mean, you compute it here, match to here, match to here, match to here, until the perturbative domain. So in this matching, they use different schemes for the coupling. It's a complicated thing, but at the end, they are able to get a good number.
As a naive, non-lattice person, my naive picture of sort of lattice scale matching is like block decimation, changing like taking some set of sites and collapsing into one. That's not the method that's being used.
Not really, no. I mean,
I don't want to take you far afield.
I can, maybe if I have time, I can explain at the end what they do for alpha S, okay?
Is lattice perturbation theory a limit at all?
Is lattice perturbation theory?
Do you need to do lattice perturbation theory?
Well, for instance, for this thing, the matching is done in the continuum, actually. I mean, you can do lattice perturbation theory,
okay. But
these schemes are usually matched to the, I mean, these quantities you extrapolate to the continuum and then you match in the continuum. So they use lattice perturbation theory or lattice continuum to do the matching.
So I think so first of all, there are several different ways.
Yeah, there are many different ways.
Determining alpha sub S with different.
Yes, I was talking about this because Andrea said that it was the most precise, right?
Just with different sets of, both hadronic quantities and then short distance quantities. And the gist is, computing a renormalized coupling that you can avoid doing lattice perturbation
Yeah.
theory, you need to match it to MS bar.
Yeah.
At some scale. And in some cases, the scales are low enough that perturbed matching is a significant or dominant uncertainty. In other cases, you avoid that entirely by doing that matching at very high scales.
But
You have to make it mild. I think you should also say that so they claim that the perturbative truncation uncertainty is under control. That's what it means by being statistics limited. But there are other calculations that work then at lower energy that have more loops. So they could be surprised by the next loop.
Yeah, you have to compute. You have to. Yeah. In principle, I think they use 2 loops in the calculation in this case.
Anything perturbative you could be surprised by the next loop.
Yeah. So this is why I was saying. I mean, some of these schemes are defined on a finite volume. So this is why I was asking yesterday whether it was possible to do these kind of tricks to compute higher orders in a finite volume scheme, right? Because it's different from the standard one.
I mean, it sounds difficult.
So there's been a lot of activity in this field also because of something that maybe you have heard of that is called the gradient flow, which is a scheme to determine the coupling in principle also. And there is a lot of activity also, people doing perturbative calculations. For instance, Harlander has been working in this particular scheme, and he has computed the matching to the MS bar up to 3 loops, I think, or something like that, but in infinite volume, not in finite volume. So there are a lot of papers here using standard techniques in perturbation theory to analyze this gradient flow thing.
You don't need the perturbative series in finite volume. Even
so you do to extract lambda MS bar. You match to the you do it differently. I'm talking about step scaling. There are many ways, right?
Then the step scaling at the end is infinite volume. It is just
At the end, yes, but the way they do it is that they simulate on finite volume down to very high energies. So if you want to define the coupling in finite volume the way they do, not the way you do, the way they do is that they match the scale of the coupling to the scale of the box, and they run with the scale of the box. So you need to define the coupling in a box. So you need perturbation theory in the box. For this particular case, if you do infinite volume, not.
But I think that they do the step scaling function, they find the beta function in steps,
Yes.
and then they convert it into the continuous beta function.
Sure.
At that point, that's an infinite volume. I believe it's an infinite volume.
No, it's a finite volume matching that they have to do.
The matching is finite volume.
No, but the expression for the... so for instance, the ratio of lambda MS bar to lambda in this scheme, you can determine at 1 loop order, and it's exact, and that's not an issue, but it's a calculation done at finite volume in principle, or with a Schrödinger functional boundary conditions on a finite volume, or twisted boundary conditions. I did that in a finite volume. So they use a Schrödinger functional boundary conditions to do the matching, and this is a finite volume determination. Sorry for the... I see now that I'm not going to finish ever, so whatever I get, it's fine, okay? This was just the introduction to what I'm going to talk about, but okay, never mind. So
what's the typical size of a lattice simulation? Meaning, what's the ratio between the size of the box and the lattice?
So typically, you go here up to, I don't know, 5 Fermi, something like that. With L.
This is in the hadronic part, but the nice thing about this, I think why Margarita didn't mention that there are finite volume effects in this case, is because the coupling is defined in a finite box.
Yeah.
So the size of the box is used in order to define
To run,
the coupling.
yeah.
So there is no error associated to the sign of the
Yes.
size of the box.
So this is for this hadronic, computing this hadronic quantity. But then, if you want to compute the running of the coupling, what they typically do is they choose mu, not mu hadronic, but the mu that runs with the coupling as a function, as 1 over a fraction of the box, right? So you simulate in a big box to determine mu hadronic, and then you go to a smaller box to run the coupling, smaller box, a smaller box, a smaller box into the perturbative domain. Okay. So in that range, you change the size of the box from the hadronic domain to tiny boxes, where the theory becomes perturbative due to asymptotic freedom. Right? I will talk during the talk a lot about finite volume quantum field theories, because using the volume as a tool to explore the quantum field theory and the non-perturbative effects in the quantum field theory is something that we do on the lattice all the time. It's very useful. And I will talk about finite volume field theories a lot during the talk, so you will see more things of that.
You asked me a simple question about normal hadronic quantities. The biggest lattice is 140 KT.
Oh, okay.
In lattice unit, I mean, in
I thought the question was the ratio between volume and the lattice.
That's right.
Okay. How many lattice points you put? Not physical, but how many lattice points? Okay, I didn't understand. Sorry. Okay, more things. Spectrum. The standard, but also exotics are starting to be. I mean, they are studying. For instance, the other day there was a mention of the double charm. Resonance that has been found recently. There's people trying to measure that on the lattice to determine whether it exists and what's its composition and things like that. And then exotics and blue balls, which are very hard. Both experimentally and on the lattice, because they mix with QQR states, and then this is a difficult issue. But there is, for instance, a very recent review by Morningstar and Heplat that you can check recent results about blue balls if you want. Quark masses.
Do you need finite volume to control the fact that it has a hadronic decay width?
Well, if you do heavy quarks or pure jam mills that you can do. They don't decay. I mean, you can define the glue balls. The problem is when you put dynamical quarks and then it's a mess because they mix. So they try to estimate the mixing, but this is complicated.
Even the exotics, they're all...
Even the exotics. Even the exotics, yeah. So before maybe going to M quarks, I should mention also scattering, now that you talk about the exotics, okay? So there's an enormous amount of work on scattering amplitudes on the lattice also, and this comes from a pioneering paper by Lucia that was mentioned also here, that was doing, as you said, 222, and this again makes use of finite volume. So you put the theory, you have the theory on a finite volume, so you cannot define asymptotic states, so you cannot define scattering, strictly speaking, but you can match the scattering amplitudes to the energy levels in the box. And this is what Lucia has done in this formula. It's called Lucia's formula. And there is a lot of work by people trying to generalize, and they have generalized, and they are using it to have to analyze three-particle scattering, decays, complicated decays, resonances, all these sorts of things. This is another very, very active area of research on the lattice. Right? And then, M quark, the masses of the quarks. This is something that Andreas also mentioned, which is done also with precision.
One of those scattering is the lattice Lorentzian?
No, that's why it's not. No, it's Euclidean always, and there is a box. So no, you cannot define the asymptotic states of the Hamiltonian, which you scatter. So there is a mapping that you can do. This is what Lucia has done, that relates the scattering amplitudes to the states of multi-particle states in the box. So there is a relation between the energy states in the box and the scattering amplitudes. And you can, extracting the energy states in the box, extract through this formula the scattering amplitudes.
Okay. Steve Sharp will be giving a talk on this next week.
Great. Yeah, Steve is one of the, he has been working on extending Lucia's formula a lot, so I'm sure he will cover all these.
At least 10 years now.
Yeah. So names, there is, by the way, a very nice review in a Lattice conference, a plenary talk in the Lattice conference by Fernando Romero Lopez on this topic that you can also check. Right? And then, yeah, quark masses, also with high precision, and many things. I mean, I will never finish. So finite temperature, lots of things, right? Which I will not cover. It's impossible, as you see. And I have not worked in these things. Well, a little bit in this, but not much. So all these with precision. I mean, we were doing in the old times what is called, as Andrea said, quench Yang-Mills theory. I mean, pure Yang-Mills theory, no fermion loops in the game. But this is not the case anymore. I mean, fermions are included dynamically in the path integral in the simulations. And this has been possible thanks to tremendous advances in computing power, but not only. I mean, people have done a really hard work and good work in devising numerical algorithms that allow to do this, right? So the precision limit now, I think, is including isospin breaking corrections. We have not been taken into account, right? So this is sort of the precision frontier now. Is isospin breaking. Which is including QED plus MU different from MD, because simulations are performed with the generate U and D quark masses, right? Typically. So there is a lot of work going on into this also. I don't know if Marina, you will talk about that also. Yes. So this is challenging, very challenging. QED is challenging both conceptually and numerically. So people is working hard to try to do that, right? So this is basically what I wanted to say about Lattice as a precision tool. And I'm going to switch now as Lattice as a theory tool to analyze theories, okay? As a theory tool, sorry, I don't know what it is. And here I'm also going to focus, on things I've been related to, not like these ones. So I apologize to the community of Lattice practitioners here, because I'm going to talk about sort of my stuff, not my stuff, but my stuff. But for instance, using Lattice as a theory tool, I don't know, Anna and Oliver have worked, for instance, a lot in studying the conformal window. So when you put many flavors in a gauge theory, you lose asymptotic freedom. At some point, there is supposed to be what is called a conformal window. Where precisely this conformal window sits was an open issue, and they have analyzed it in very big detail on the Lattice. Very good work there also. And for instance, supersymmetry. This is very tough on the Lattice, because the Lattice breaks supersymmetry, okay? You have a discrete set. And there's been a lot of work in the, I don't see Simon here, but Simon, for instance, has also worked in trying to devise ways to handle supersymmetry on the Lattice in efficient ways, right? And there is a lot of theoretical work. You have also done a lot of theory work. But I'm going to focus on things that...
Sometime I should tell you about doing this all on curved manifolds for conformal field theory.
Conformal field theories, yes.
Making progress, I think.
Yes. Yes.
Go ahead.
Right. So, yeah, you should invite somebody, all the people to give lectures if you want to cover it all, which I cannot do. But I'm going to focus on two things that there's been a lot of work on the Lattice too, which is large N, and also related to this finite volume things, because I have worked in these things, and also because there is kind of a revival of some ideas that have been in the community for very long, also in the TH community. So there are things that maybe ring a bell for some of you, like generalized global symmetries. or volume independence, or adiabatic continuity. I will talk about a little bit about these things later on. Which there are a lot of relation with things that people have been doing in the lattice since very long ago, right? So there is a person in the HEPTH community that has been trying to bring these things together, is Eric Poppitz, and he has a paper that in the title has something like pouring new wine into old bottles. So I am the old bottle. So I'm going to present the old bottle perspective to this topic, okay? But before doing that, let me talk a little bit first. So I'm going to do the following. The plan is the following. I'm going to first talk about a little bit about the thing that theory thing that the lattice is good for, which is analyzing confinement. So I will talk a little bit about what has been done for confinement in very general terms, very basic. Okay. Then for the non-experts, I will do a very fast, and sorry to the experts, lattice essentials thing for you to know how we do lattice. Then large N on the lattice. And if I have time in the afternoon, which we will see, finite volume gauge theories, both continuum and lattice, okay? A combination of both. So let me start with confinement, which is basically what boosted from the beginning, the study of confinement, what boosted from the beginning the use of lattice gauge theories as a theory tool to investigate things in quantum field theories, right? Okay, so in the 70s, when Wilson started lattice gauge theories, the basic result that can be obtained in the back of an envelope, it's very easy to derive, is the fact that Yang-Mills confines at a strong coupling on the lattice. Okay, if you do a strong coupling on the lattice, which means that the bare coupling of the theory, let me put it like this, goes to infinity, and you use the lattice theory, it is very easy to derive that the theory develops a string tension, something like, I think it's log ng squared for SUN of this sort, where this is the lattice spacing. I will talk about that in a moment. And this is very easy to do. If you have a Wilson loop like this, the basic contribution to the Wilson loop comes from tiling the Wilson loop with small plaquettes, we call, and that gives you directly an area law for the Wilson loop without a string tension. Okay? The problem is that this limit is the opposite to the limit where physics lives. We call it the continuum limit, and this limit is precisely G0 to 0. Okay? So it's not obvious that you can translate this result. I mean, you can go further in the strong coupling expansion, but it's not obvious that you can translate this result to this limit. And for instance, this derivation is independent of the fact that the theory is non-abelian or not. So if you do it for a U1 theory, you get the same string tension and confinement in a strong coupling for the abelian theory. Okay? But for the abelian theory in 4 dimensions, we know that if we study the theory as a function of the coupling, there is a phase transition that separates strong coupling from weak coupling. QED is not confined, okay? It's not confining, okay? So this shows that just having strong coupling confinement is not a proof of confinement or anything. Okay? But, I mean, this was very important when lattice field theories started to play.
Is there more evidence? I mean, I give this, argument in my graduate course, and then
Yes.
And then the answer sort of is, in the UN case, we know the answer in the continuum, so we know there must be a phase transition. Is there more evidence actually for the existence of a phase transition?
For U1.
Like if you take
For U1, there have been simulations in the very old times, determining the existence of the phase transition.
Also, analytic arguments. The last paper Alan Guth wrote before he went to cosmological things was on the phase transition in the
And then there's also like absence of, so then there's clear reasons why similar arguments are irrelevant to this.
Isn't it still unknown whether there's a second order phase transition?
There was a big debate about that in the early, in the 2000s, but I don't know.
There might be a new field theory at that phase transition, but I think that's still not decided. Is that right?
It's unlikely. I think
It's unlikely.
I think it's very far.
Like we never know, but nobody found a second order phase transition yet.
I mean, if it's first order, that's usually, that was relatively easy to tell. Unless it's first order with a very small jump in the order parameter.
You're talking about whether that line ends somewhere.
Yeah.
At a second order.
Yeah, exactly.
Okay, so but the lattice has I mean, on the lattice you can measure the Wilson loop directly in the continuum limit. So you can measure it and show the following. I mean, Andreas also had this plot in his talks. So if you plot the energy of a Q-bar pair as a function of the separation between the pair, what you can measure on the lattice for heavy quarks is something that is Coulomb here due to asymptotic freedom, okay? And is linearly rising here with the string tension given by this, in this way. This is for infinitely heavy quarks, or if you want for pure Yang-Mills. But we know that if you put dynamical quarks in the game, the string is going to break, right? So this has also been measured on the lattice. So if you put here, for instance, the 2 meson threshold, what the people observe is that the curve goes like that, right? This is a very challenging calculation because, I mean, you really have to cook a basis of states, very complicated, that contains the 2 meson and allows you to determine this. Yes?
Maybe you're going to say it, but the first excitation is flat and then it goes along the line.
I was not going to say it, but yeah, you have that. Yeah. So you have to separate the 2 states, which is very complicated, right?
So the string is somehow still there.
Yeah, it is still there, but in excited states. Yeah, this is true. So I don't know who measured this for the first time, the string breaking. I think it was measured for the first time for a joint, which are not confined. Maybe Bali, I don't remember. Bali. I think it was Bali in the 2000s or so. Yeah. And then there is a paper by Bulava recent, which they really make it very precise. Yeah. Yeah. So they have plots of all these things. So you would have other meson states, other threshold, other things, and then the string continues as an excited state. This is true. Okay. So this is not a proof, mathematical proof. This would not win the $1 million prize.
$1 million is actually for proving that
Yang-Mills mass gap has a mass gap, yeah, not for proving this. Has a mass gap, right. But it has been studied with a lot of detail on the lattice. Okay? Sorry? Sorry?
The mass level here, the constant energy there. It's in some sense measuring the lambda that's added to a uniform mass to get the meson state.
No. This is just 2 times lightest mass in the spectrum. So 2m pi, for instance.
Well, 2D metons.
Whatever you put there. So you have the string, no? And at some point it breaks, and then you have the two mesons, right? Whatever mass they have in your simulation.
But they are heavy light, right?
Yeah.
Ah, they are heavy light. Well, because these are probes. Because these are probes. Yeah.
And little b plus lambda.
Yeah. This is what you were saying. Okay.
How you can measure lambda non-perturbatively, but maybe I'm missing something.
Yeah, it's more complicated.
Okay.
I don't know. Yeah, these are probes. You're right. So these are heavy and these are light. Yeah, this is true. Okay, so people have also measured looked at the string, at the flux that forms between quark and antiquark, and analyzed the shape and the width and the properties of the string. Okay, and if you want, also for 3 quark potential. So if you want to look at nice pictures of this, Derek, I never know how to say the name, Lane-Weber, or what is? Yeah? That's right. Has very nice pictures in his webpage that you can look at of all these things, okay? Still, something that we would like is to have a microscopic description of these things, and this is tough. I mean, no success from the lattice, I would say, there. So, so there have been many games around in town, monopoles, vortices, instantons, fractional instantons, lots of things that people look at on the lattice, trying to identify what of those things generate confinement. The time you get to the IR, it's a mess, because the whole thing becomes dense, and you don't know what really to do. So it's a very complicated game, fun. I have also played that game a lot. But I cannot say that there are sharp conclusions there, because it's very tough. Okay.
Most of these objects you would expect maybe in some semi-classical limit.
Yes. So
I'm better at large n.
Yeah. So I'm going to talk a little bit about these things later on. So how to make the semi-classics visible in a controllable way. But that you can do, for instance, what I'm going to talk about is putting the theory in a small box, and then you can control with the size of the box when you enter the semi-classics regime, and you can control the objects in that regime. But the objects in that regime are sort of determined by the box itself. So it's very difficult to connect with the infinite volume domain, because all these objects become very dense once you enter lambda QCD domain, right? So it's a very difficult game.
There's a weird paper by Wilczek to suggest putting this in an ADS box, which he says to the second scales.
Maybe. No, but can you put an ADS box in the lattice, on the lattice?
Yes.
Yeah? Do it. Yeah. So, okay, so I'm not going to talk about these things, although I will talk a little bit about how to make semi-classics visible, right, in some sense. So what I'm going to do, as I said, is talk a little bit for the non-experts about lattice essentials. Maybe you all know, and then I don't have to do it, I don't know. Who knows nothing about how we do things on the lattice? Okay, I go on. So then I will talk a little bit about large N results on the lattice. And in the afternoon, I will go on to the finite volume and the semi-classics and these kind of things. Okay. So I still have 45 or what? So essentials, lattice essentials, right? It's going to be really basic, just a few flashes of what you need, okay? So this you all know. What we do is discretize space-time on a lattice. The lattice spacing, we typically call it A, and it's the only dimensionful quantity that is going to be here from now on, okay? Everything else is going to be measured in these units. So putting things on a lattice, for the moment I'm assuming the lattice is infinite, regulates the theory, puts an ultraviolet cutoff. One way to see this is if all my coordinates will be an integral times the lattice spacing, right? And if I do a Fourier transform, I would have phases of this form, which means that functions will be periodic. Like this, right? So the momenta are limited to live on a box also, which is called the Brillouin zone, which sets an ultraviolet cutoff that is given by pi over A, right? So all momentum integrals are cut off at pi over A, and this is the regulator, okay? This is how the lattice puts a regulator. So the theory has to live in the continuum limit when I go to 0, and this brings the regulator to infinity, okay? So now we want to have, I'm going to focus on Yang-Mills theories, and we want to define a gauge invariant action for fermions and gauge fields on the lattice. And the basic building block, the only thing you need is parallel transport. This is the only thing you need, right? So imagine that I want to define a covariant derivative, discretized one, acting over a field. An ordinary derivative is defined as the limit when A goes to 0. I have to take finite difference over A. But this is not covariant, okay? It doesn't have the good gauge invariant properties. You can make it covariant by putting here something that is the parallel transport of the gauge field. So this is a path order exponential between x, ig, okay? So this is an object that transports the gauge field between x and x plus a mu, and we represent it here like this. We call it a link. And it's an element that lives on the group, not on the algebra. It's an SUN element that lives on the group, okay? And then other fields like fermions or the scalars live on the sides. Okay? So now it's very easy to construct the gauge invariant actions using the parallel transporter. You only have to do a closed loop. So the trace of a closed loop is gauge invariant. So with the trace of any closed loop, you can make a lattice action. And the simplest one is the one that was done by Wilson, which is just a plaquette. The smallest loop in the box. But this is not the only possibility. I mean, you can construct lattice actions with 2 by 2 loops, 1 by 2, many other things. And indeed, this is a very useful way to control what we call lattice artifacts. I mean, corrections to the continuum physics due to lattice artifacts. And there is a whole program of, it's called semantic improvement, combining different loops to reduce the amount of lattice artifacts that you have in a lattice simulation. Okay? But in principle, the simplest lattice action is this one, which is the Wilson action, for which the action, I will write it in a way that is useful for large n, using Toft coupling. Sum over n, sum over mu nu, and the trace identity minus the plaquette. Real trace. Okay? So it is very easy to check if you insert in the plaquette this expression for the gauge links, that this action in the continuum limit at a classical level reproduces the a to the 4th sum over x, sum over mu, f mu nu a, f mu nu a. And this is the integral, right? Plus corrections. Okay. So this is a naive continuum limit, and for the fermions, in principle, you could do the usual. I mean, you could construct a fermion action in this way, using this covariant derivative. But the problem, and this, I'm sorry, I have no time to discuss about it, is that if you look at this lattice propagator, it does not describe one fermion. If you look at the dispersion relation, it has 16 fermions attached to it. So it has a fermion at 0, relativistic fermion here, but also in the corner of the Brillouin zone, there is another one identical. Okay? So there are solutions to this, and if you were here in Simon Scatterall's talk, he described well, the basics of this and also how to possible ways of constructing actions that don't have this problem. These are called the doublers, right? Okay, so
a question, because it was already alluded to, but do people ever try to put the lattice in a different geometry, like a sphere? Or
yes,
that's what I do.
this is what he does.
It's hard, but it's making progress.
Yes.
Okay. Because it's conformally flat, so I was just curious about how the sphere appears. And,
I mean, in one word, the problem is that your cutoff A varies around the sphere. So you need to do the geometry and the coupling constants very carefully to compensate for this variable cutoff. And that's a hard problem, but it's, I think, a problem that you can make progress on.
There is also people that have done gravity numerically using lattice triangulations, but
There's one solution to doing the conformal field theory on a sphere that seems to be working.
Interesting.
So the lattice breaks, of course, Lorentz invariance. But the nice thing of this square lattice is that it's recovered as an accidental symmetry in the continuum limit automatically, right? Basically, because all the, due to the cubic invariance, all the operators that break Lorentz invariance are higher order, higher dimensional operators that disappear in the continuum limit. Okay. So.
You get an infinite subgroup of the translations from the story of the lattice, which is very useful. Right?
What if I have a chiral gauge theory?
We don't have a chiral gauge
Don't have that, right?
We don't have that. So this works. Yeah. Yeah. So we have this working for vector theories.
Does he have one?
No.
He doesn't have one, he has ideas.
Several people, they're interesting ideas.
Yeah.
So David Kaplan's coming to the conference.
Yeah. David has a new proposal of doing domain walls on a circle, which has also issues, as far as I know. Yeah.
Let's let you continue.
It doesn't matter. So what do we do with this? I mean, we typically also put this thing on a box, and then we have a finite set of degrees of freedom. We put it, I mean, this is an Euclidean box, right? So basically, if you want to compute an observable, what you do is beta is 1 over the temperature. It's basically the time extent of the Euclidean box. And we have to compute this thing in the limit in which beta goes to infinity. If you want to have 0 temperature physics, you can also do finite temperature physics, and it has been done in this way. Right? So basically, what we use is the representation of this thing in a path integral formulation. So basically, you have two path integrals weighted with an action, with the Euclidean action. But these are ordinary integrals because we have this discrete set of variables, so it's a well-defined path integral. Okay, but the number of degrees of freedom is humongous. I mean, it's, you cannot really do these integrals by hand, so you put them on a computer, and then you simulate them. I mean, you do the integrals with a Monte Carlo, something that people also do, and generate configurations with the Monte Carlo weighted by this weight. So here you see already why we have problems in some cases, because if the action is complex and not real, this is not a measure, and then we cannot easily do these things. So for instance, real-time evolution is an issue. It has been mentioned already here. Chemical potential is an issue. It can be done if the chemical potential is small, but not otherwise. Theta dependence in Jamil's theory is an issue, because it's also a complex determine the action. So there are things that we cannot easily do, only as Taylor expansions, if you want, approximations close to theta equals 0 or close to mu equals 0. And to finish these essentials...
So another question, do you need to gauge fix or not?
No, you don't have to gauge fix. You only have to gauge fix if you insist on doing perturbation theory. If you want to do perturbation theory on the lattice and you want to define a propagator, you have to, for the gauge field, you have to gauge fix. But the lattice does not require gauge fixing. Okay? So you compute these observables. If you insert here a gauge invariant observable, you forget about gauge fixing. Okay? So no gauge fixing required.
You also just said that you didn't understand the papers on gauge fixing. I understand like that, so he was forced to formulate QCD on the lattice.
Oh, that was the reason he formulated QCD on the lattice? Okay. So continuum limit, and then I finish with the essentials. We have to take the continuum limit. I mean, we don't live on a lattice. We have to take A to 0. And where is the continuum limit for lattice theory? So imagine that I want to compute, I told you that the only dimensionful quantity is the lattice spacing, and all variables are determined on the lattice in terms of the lattice spacing. For instance, if I want to compute a mass, what I do is to compute a two-point function, right? So if I use a spectral representation for the two-point function, it would be a sum over states, the energy of the states, times the time, but the time is discrete. So here I have the lattice spacing times the number of sites in the time direction, and then this coefficient, okay? So what appears here is the energy of the states in units of A. If I take the large time separation of this correlator and I fix this to 0 momentum in space, at infinite time what I will get is the mass of the lowest state. So the lattice mass is the continuum mass times the lattice spacing plus corrections, right? So you see immediately here what happens when I take the A to 0 limit. The physical mass is a physical mass, a number that is fixed, right? So if I take the A to 0 limit, all lattice masses will go to 0 in this limit. Which implies that the correlation length of the system, which is the inverse of the lightest mass in the system, goes to infinity, right? And this defines second-order phase transitions. So the continuum limit for the lattice live at critical points of second-order nature. And we have to look for second-order critical points in order to take the continuum limit of the lattice action, okay? So just to finish, where is the continuum limit for the gauge theory? And for that, I will use a simple relation between lambda and, which is an renormalization group invariant quantity. I can write it like this, 2V0 lambda. Okay. So if I take mu to be the lattice cutoff, and I want to send it to infinity, keeping lambda QCD fixed, which is a physical quantity, you see immediately that I have to send the Baire coupling of the lattice theory to 0. Right? So for the Piojan-Mills theory, the critical point where I have to define the continuum limit of the lattice, this defines the quantum field theory in the continuum, is Baire coupling to 0. Okay? So once I do this, I have no free parameters left in there except for the quark masses. So if I set quark masses to 0, the theory is fully predictive, and this is one of the beautiful things of asymptotically free theories, right? So any ratio of masses is fully determined with no free parameters, okay, in these theories. Okay. Any questions, or I continue to the last part? No? Okay. This was very basic, sorry, but, well, for the people that knew nothing about this, if there was any. with fermions, I don't know. Do you know, Andreas? Maybe you know. How it scales with the number of sites with fermions.
So, I mean, you're stuck with an exponent of 4, because we were in 4 dimensions, and then it's 5 and 6. So, you're talking lattice spacing 8 to the minus pi to 6, but some of the algorithms also depend on the total number of sites to the volume. And I think that's space-time volume of 5/4, so the number of sites to the 5th.
So one of the issues nowadays also is that if you get very close to the continuum limit, close to the critical point, there is critical slowing down, of course.
Yeah,
so it becomes, this is what you were saying. So it gets tougher and tougher and tougher. And there is one issue in particular that is worrisome, that is the fact that... Yeah, I know.
And in thermodynamics, the effective exponent is much bigger. So even though in thermodynamics the time direction is small, in some sense, the scaling properties are worse. But I've forgotten what that is.
Since I try to explain this to my non-lattice colleagues, the Hilbert space is exponential. Right? You start to do the path integral without approximations, without Monte Carlo. It's an exponential problem. So the amazing thing is that the Monte Carlo turns this into a polynomial problem. From a computational point of view, we took an exponential problem and turned it into a polynomial problem. And that's this discussion about what that polynomial is, how many factors of x. But the fact that it is a polynomial. It's a volume, it's a critical slowing down.
I think we answered David's question.
But the point is, it is polynomial. And that's what makes it.
Let's move on. Rich, let's move on.
Okay. So let me go a little bit, not in very detail, but to Lagen on the lattice. Well, you all, I don't have probably, I'm not going to explain any of this. But Toft showed us that small parameter in these theories is 1/n with n the number of colors, okay? And n equals 3, maybe small in principle, 1/n equals 3. And people in the lattice typically look at what is called the Toft limit, in which you send n to infinity, keeping nf fixed. So this goes to 0, and this is what is called the Toft limit. And in this limit, if you use the counting rules of Lagen gauge theories, fermion loops are suppressed with respect to gluons, and then the theory is quenched. There are no dynamical fermion loops in the gauge, right? So most of the people looking at this problem on the lattice do directly the quenched simulations, although, as you will see, some of the n values that people reach are very small, and then it's debatable whether an f over n you can consider small or not. Okay? So there are two types of approaches to do Lagen on the lattice. One of them that I would call the standard approach consists on simulating at various values of n and then extrapolating. So typically people do 2, 3, 4, 5, order 10 at most, okay? Because matrices are big and it's sort of tough. And then they extrapolate results to n equals to infinity. And there are, I don't know, enormous number of results on the lattice doing these kind of things, including meson and global spectrum, string excitations, theta dependence at small theta, or topological susceptibility. Also finite t, very many things. And this is a very active area of research there. Also recently, meson-meson scattering, people is looking at this. But So there are many results here. I recommend you two reviews on this topic by Panero and Lucchini, and more recently Hernandez and Romero Lopez. Okay. And dealing with this issue of whether you can neglect or not the fermions, the dynamical fermions, there are a lot of works here by Tom de Grand, including dynamical fermions in the game and analyzing the size of these simulations, of these corrections, and also by Hernandez et al. So what I'm going to focus more here, because I have worked on that, is an alternative approach that dates to the 70s. It's really very old, which is, goes under the name of Eguchi-Kawai reduction. So what remains of this first lecture, I'm going to describe a little bit what is Eguchi-Kawai reduction. It's, as I say, a very, very old idea. It was proposed in the 80s. You don't think it's very old? No? Okay. Well, 80s. I was doing my PhD in the 80s, so at the late 80s. It was established there. It's I think it's a beautiful idea, because basically it tells you that you can simulate your theory in a lattice that has one single point, only one point, when n is large. Okay? So you replace an infinite volume lattice with infinite number of points with just one point, a matrix model defining that point, which is amazing. I mean, that would work. Hypercube. Yeah, so 4 matrices, if you are in 4 dimensions, you can be in 2 also, no? Which there works, but as you know. So this was proposed in this time. Immediately when it was proposed, even in the paper that proposed the idea, there was a footnote saying that it doesn't work as it was originally proposed, right? But then there appeared 2 fixes. One of them was Banot, Heller, and Neuberger, and also Gross Kitazawa studied this problem, which was called quenched Eguchi-Kawai reduction. And there was an alternative that was called twisted Eguchi-Kawai reduction by González Arroyo and Okawa. Okay? So apparently the thing was fixed until the late 2000s, 2009, 2010, when people started to do numerical simulations of the theory, massive numerical simulations of the theory, and saw that the original proposals by Keck and Tech failed, were not working. I will tell you why they didn't work in a moment, okay? So this, put the people that were having these ideas to work again, and they found fixes to the problem, both in Tech, and Neuberger claims he also has a fix for Keck. So I'm going to describe a little bit what is the idea, starting from the very beginning, right, and tell you what has been done. I've been involved in using Tech for many things, so from computing meson spectra, running of the coupling, chiral condensates, and the last thing we have done is the Gluino condensate in n=1 super-Yang Mills, which one of my collaborators, Claudio Bonanno, is going to be here in March, and I think he will give a talk on this topic, and you can, I'm not going to describe this work. You can look at Claudio's talk, okay?
One of the problems with Eguchi-Kawai really is bugged me. I'm just interested in if there's been any progress, which is the 1/n correction.
It cannot give the 1/n corrections.
Well,
in principle.
I'm sure it can.
Yeah, but you have to work harder.
No,
I
know no way of doing 1/n correction systematically.
The thing is that the standard 1/n corrections in at least twisted Eguchi-Kawai are finite volume corrections.
Yeah.
not of the same nature as the one over n corrections you want to look at.
Right.
And it's difficult to disentangle. So in principle, this...
Anybody figured out how to...
So it is an open issue. For instance, we cannot do glue balls yet.
Right, exactly.
We cannot do topological susceptibility yet. So for that, it stays at the same level as it was in the 70s. Yeah, we cannot do that. We can try different things, but it's not easy. Yeah, it's annoying.
Sounding to have an approximation which is supposedly exact.
In principle, it gives you the Wilson loops exact, so it should be possible to construct. Yeah, yeah, that's right.
Limiting algorithm without any ability to calculate.
The corrections. I agree.
Very strange.
I agree.
Very conceptually.
So maybe, yeah.
There's no ideas of doing glue balls.
Right?
There's no idea.
In principle, you could.
Now, there are good reasons why they fail.
I know it's hard.
Except for the what? Yeah. Anyway, but this is too technical. Doesn't even explain language information.
So in principle, you could reduce only the three-dimensional box and keep time infinite. That could give you the glue balls, right? In principle, that could give you the glue balls, but it's not obvious. I mean, it has not been tried, so I don't know. So what is a Gucci-Kawai reduction? I have said to you that it's replacing. This is an infinite volume box by a one-side box. And the claim is that they are equivalent. I mean, here I have 4 matrices. Well, I only can draw 3, just the links, right? So you replace the n-dependent links by just a matrix. And they are equivalent in the large n limit. Okay? So I'm going to show to you how this equivalence goes, which uses the loop equations. Okay? So the loop equations are, at least on the lattice, due to Migdal and Makenko. And it goes in this way. So I'm going to compute a Wilson loop. I'm going to start from a Wilson loop in the original lattice. Okay? Something like this. Let me consider 2 by 2 to simplify. And I'm going to compute the trace, the expectation value of the trace of this Wilson loop with a generator of the Lie algebra here inserted. Okay? And I'm going to do a change of variables to derive the Swinger-Dyson equations associated to this operator. So I'm going to change the link in this way. I have x here still. Okay. So you derive the Wilson-Dyson equations, which is basically equivalent to say that the variation of this operator plus the variation of the action times the operator is equals to 0, right? So if you work it out using the relations between the TAs, the result is the following. You have a term here that is the expectation value of the original loop, and then you have corrections to this that go like this, and then I have a trace of the loop where here I insert a plaquette like this, right? That comes from the action. And there is another term where I have this, right? So I'm writing an equation for the loops. I mean, this reduces to an equation for the loops. Now, there is a special case where this is not so simple, and it's when you have loops in which one link is repeated more than one time. So if I have a loop of this sort, for instance, okay, where this link is repeated twice, let me call this C1 and this C2, this will generate a term that goes like the Wilson loop, the trace of the Wilson loop at C1, the trace of the Wilson loop at C2, right? This is not a Wilson loop, but if I use large n factorization, this goes back to the two traces. Okay? which is again Wilson loops. Okay, so in the original lattice, in the larger limit, I have a set of closed equations written in terms of Wilson loops, and everything, in principle, I can construct in terms of Wilson loops, so I have the physics there, right? So what happens on the reduced lattice? If I do the same trick on the reduced lattice. Okay. So on the reduced lattice, let me do the plaquette, for instance, which is the simplest. I just have the four matrices, U mu, U nu, U mu dagger, U nu dagger, right? So in each of these loops in the reduced lattices, necessarily, the links are repeated, okay? So if I insert, for instance, the TA here, I will get from here source terms like those ones that would go like trace these for, well, whatever. These, for instance, well, I will use already factorization, trace of this. Okay? So these loops in the original lattice are open loops. They do not close like the Wilson loops. So in principle, by gauge invariance, they are 0, and they are not there in the theory. But on the reduced lattice has periodic boundary conditions. So this is a closed loop, this is a closed loop, and this is a closed loop. So in principle, it is not 0 by any means. The only way in which it would be 0 is because there is a symmetry that you can try, a symmetry of the classical action, in which you replace each link by a center element times the link. So if center symmetry is preserved in the theory, these loops will average to 0, and then you recover the original loop equations. So the loop equations in the reduced lattices are identical to the loop equations in the original lattice, so the two theories are equivalent. Okay? What is the problem? That this symmetry, the set n to the d symmetry that you are supposed to have for this to work, in 4 dimensions is spontaneously broken with periodic boundary conditions. Okay? So with PVC, this is spontaneously broken. And this is what Banor, Heller, and Neuberger found out, and this is the footnote that was there when Neguchi-Kawai published that paper saying, beware that this can be spontaneously broken. Okay? And then it doesn't work. So the reason why it doesn't work, why it's spontaneously broken, is very similar to what happens at finite temperature. If you compute at finite temperature the one loop effective potential, the minima sit at Polyakov loops that are proportional to the center elements of the group, right? And the center elements of the group are not traceless and break the symmetry. So in Neguchi-Kawai, it's basically the same. If you look at the zero action configurations, and you compute quantum fluctuations around those, the quantum fluctuations select as minima configurations where the symmetry is broken. Okay? So there is a spontaneous symmetry breaking in principle in the weak coupling limit. Okay? In strong coupling, this works, but there is a phase transition that separates, in this case, at large n, the reduced model at strong coupling from weak coupling. So it's an issue. So the fixes that were done at the time had to do precisely with this. One of them was if you have a solution of a minima of the action, you can write it as an angle, diagonal of constant angles. And the solution was basically what is called KEK, quench Neguchi-Kawai, was basically to freeze the angles in such a way that the symmetry is restored. Because basically what happens when you compute the quantum fluctuations is that the angles want to be all equal, and then you break the symmetry, right?
Okay,
when you calculate observables? You average a posteriori. So you first average over the things that bring you to the diagonal, and then you average over the angles with a symmetric distribution. That was the idea. So the idea of twisted Neguchi-Kawai was instead to change the boundary conditions to something that is called Toft twisted boundary conditions, that I will discuss a little bit in the afternoon, which basically guarantee that the vacuum configuration is traceless, and all loops in the vacuum configurations are traceless, and then the symmetry is not broken. Okay? So, well, I told you already the story that this These were the original ideas. This failed. Basically, you were saying that, you diagonalize this, and first you average over this. The problem that was seen in the simulations is that this induces permutations of the angles, and that brings back the problem. So Neuberger says now that he has a fix to Keck that consists on basically freezing also the permutations, but there are no numerical simulations, as far as I know, doing that. And in the case of Keck, the trick has been to modify slightly the boundary conditions with respect to the original thing. So in the afternoon, when I talk about finite volume things and semi-classics, I will try to explain a little bit why the original version of Keck failed, which can be understood also in terms of continuum physics, not lattice physics. Okay. So one man.